This is part 2 of our online scripting class. Today we're going to be going over registers, the system memory, and how to use those. We're also going to cover communications, and time permitting, we're going to get into image and product objects, which give you more advanced control of the system and open up a lot of parameters that you wouldn't have had otherwise. I'm going to go ahead and open up PowerPoint here. Are you guys able to see this? Is anybody not able to see the slides right now? Okay, I'll keep going. Okay, so we're going to talk about registers first. Same format as the last class. I'm going to throw a lot of information at you, and then we're going to work through it in examples. So for this module on registers, we're going to go over the common uses for them, the structure and the architecture of our registers, and the various register tag formats, and what a tag is, if you guys aren't familiar with that. The registers are just part of the system memory, and they're used to store data. Specifically for those of you setting up the inspections, they're there just for any data you need to store. Variables and other data can be stored and accessed by any script, whether foreground or background. So just keep in mind that both types of scripts have access to these. Data can also be transferred to or populated by external devices such as PLCs. Like with the other various parts of scripting, you do have to keep in mind the data types you're using. Okay, by default, registers are cleared every time the camera is powered up. We call them volatile memory. They're there as long as the RAM is still current and fresh, but when the RAM, when the camera is powered down, the RAM's cleared, and therefore your registers are, any data that was in them is cleared. However, you can save the data to registers. You just need to do it via a script, and we can go over that at the end of this. Okay, so here's a good sample schematic of the DVT registers. Over here in the pink,
I think I remember seeing a Moto Man.
over here in the pink, we've got the reserved registers, and these are for the DVT registers. The reserved registers are 0 to 31, so those are taken out. You cannot write to them. But if you're trying to access them with Modbus, it's the same set of registers with the same data. You just access them with registers 0 through 15. And the reason for that is that the DVT registers are 8-bit registers. I apologize. And the Modbus registers are 16-bit registers. So one Modbus register encompasses 2 DVT registers. So this is the same space. You just have 2 different ways of accessing it. And then this dotted line kind of breaks off what you cannot write to, this reserved memory over here, and what's available to you, which are registers 32 through 16,383. You've got plenty of room to store data, and it's the same thing here. 2 registers are the same thing, make up one Modbus register. However, it's different in this case, and different from Framework, where the DVT register space and the Modbus register space was the same as it is here, and you would access register 31, say, in Modbus with register 15. Here we've given 2 different parts of the memory, so the Modbus registers are completely independent of the DVT registers. So if you were to store something in Modbus register 16, you could not go into DVT register 32 and access that data. They're not shared, they're independent here. However, the Modbus registers are still 16-bit while the DDT registers are 8-bit. So this memory is shared by BEST and DDT. You can access the same data, and here it's not shared to independent places to store data. Okay, and then the tags allow you to move, monitor, or set data within the system without the need of scripting. Because the registers, when you view them in the system communications window, oftentimes the data that you're seeing in that window doesn't make any sense to you. It's not the number or the string that you were trying to put into those registers. So we created a tag to kind of interpret that, that data for us. And tags can have 5 purposes. With the monitor purpose, you just view the values in the register space. With the literal, you can set a register to a constant value. So if you need to write to register 200 real quick to see if a script is working and getting the data out of 200, register 200 correctly, you can use the literal tag. The sensor tag is used to move data from an inspection sensor to a register space. So it just grabs it for you. You don't need to go into the script to get it and then write it to a register. The system, very much like the sensor, it just moves the system data to a register space, and then the product, same thing, moves the product data to a register space. Okay, so some kind of pitfalls here, or some things to remember, are you need to keep track of how many registers a specific data type uses. You can write over part of the data and corrupt it. For instance, if you write a double to registers 100 through 103, then write a double to registers 102 through 109, the data in registers 100 and 101 will be unintelligible. You won't be able to tell what it is. The safe rule, like making every variable double, the other kind of cardinal rule with this is to skip 10 registers between each variable. So write something to register 100, then go to 110 and write something else, 120, write something else. However, with strings, each character, including spaces, take up 1 register. So we need to calculate those out specifically. Okay, so let's get into some examples real quick. Do you guys have any questions before I get started?
Nope. Jennifer?
Uh-huh.
Is your resolution really high?
I do have a high resolution.
Because I can only see I can see about 3/4 of your screen, but I gotta keep scrolling back and forth to see the edges.
Okay. Let me try something. I just do it like this. How's that? Is that better?
Yeah. But for the intellect, it might give us the same problem as yesterday.
Yeah.
What was the problem yesterday with intellect?
I can only see about half the screen.
About half the screen? Okay.
Was anybody else having that problem?
Yeah.
Okay. All right. I am probably going to need to mute you guys again, but again, to unmute, if you can't see anything, press *7.
Okay.
Okay, but I'll resize intellect as well.
Perfect, thanks.
Thank you.
No problem. Okay, so let's go into intellect. Okay, how is this looking? Can you guys see all of this?
Almost.
Almost.
Almost? Is it vertically or horizontally?
Horizontally.
Finally.
Okay, so how's that?
That's
Okay,
good.
Yep, pretty much.
great. Awesome.
Great.
Okay. Okay, so the first example I have here is just passing information between background and foreground scripts using the registers. So in the background script with this, we want to store, I guess we have a sensor on here calculating an angle. Okay, yeah, we've got an object locate sensor locating this, and we can calculate an angle on this soldier guy's rotation. So in the background script, we're going to store the high and low angle limits, basically how much in either direction this guy can rotate. And we're going to do this, we're going to write these values in the background script and then send them to registers. And our foreground script is going to get them from the register, compare the measured angle to the limits, and cause the script to pass or fail based on whether or not it's rotated too much. And one of the advantages to doing it this way is just you can change it on the fly. Instead of actually stopping inspections and going into your product and opening up the foreground script and editing what these limits are, you don't need to interfere with the inspections on your camera because the background scripts are not dependent on inspection. So if this was running and you just needed to say, oh, we can add 5 degrees clockwise, you could go into your background script and just change that value and update the script, and it will change it on the fly. So that's kind of a tidbit of how you can kind of streamline your system to work a little bit better and smarter for you. Okay, so I'm going to work on the background script first. So again, I'm going to come to System, and I'm going to open up the System Explorer window. And in that, I'm going to open up background scripts. Okay, so I've already got these variables declared and values assigned to them. I've got a high angle and a low angle, negative 15 degrees and 15 degrees. That's what I've got. And now I just need to write them to registers. So to do that, just real simple, one line of code. I'm going to come into the functions window over here and just double click so I don't have to type everything out. And because I'm using doubles, I'm going to go to register write double. And the first input it wants is the register to write to. And again, because we have 8-bit registers, but these variable types, I believe double takes up 64 bits, it's going to actually write from like register 100 to 107. So this is just the starting register that we're entering here. And just the variable name. And the same thing for the other variable. But I'm going to skip 10 registers. Capitalization is important. Okay, real simple, no errors. And then for the foreground script, we're just going to get these values. Out of the registers using register read double. Okay, then I'm just going to input some if statements to evaluate whether or not we're high or low. I'm just going to use that with conditional. I'm going to say one thing I've actually run into myself a lot is I go to make a result fail, as in here I'm accessing the result attribute of this sensor, whatever it is, and I'm trying to make it fail. However, I can only do that for the script soft sensor because I have access to all of these containers and I can write to them. And the commandeer object and any other sensor I have in here, they're read only. So you get an error when you're trying to, each one of them has results. So if I had commandeer object dot result equals fail, I would get an error saying can't do that, it's read only. It's usually just that I grabbed the wrong sensor dot result. So that's something I actually run into myself quite a bit. And I'm just going to input one more. Okay, and then I've already written the actual angle from the inspection to the distance container for this sensor, and I've also got a string that's going to output these values to the result table. And I'm failing the soft sensor if either of these fail. So let's compile, apply. So I'm getting, see, this is what our actual angle was from the inspection and what the high and low angles are. And those have not changed because I haven't run the script yet. So let's do that now. Then come over to the background script, right click on it and press start script. Let's see if that works. Oh, you know what? It did work. It just didn't update and show me that it had run. Let's advance to the next image, and we can see here that that script did run. I was expecting it to be a continuous loop, like we talked about yesterday with the while true statement. However, we didn't have that in there, and it ran so quickly. There's no loop in here, so it ran so quickly and deposited these values into these registers that it didn't update and never show me that it had run. But I can tell that it had run because we pulled the values out of the registers here. Okay, so we've got the 35, which is too high, so we're failing. And we're failing, and we're passing. Okay, so this is just a real basic example where in the background script we're writing values to registers, and in the foreground script we're grabbing them and manipulating them with data, and then we're applying some of the stuff that we talked about yesterday with failing scripts by accessing their result parameter, and then outputting the data to the result table. Any questions before I move on? All right. Open up the next example. I need to go ahead and change emulators. And I need to change emulators again. Oh. Change back to bitmap. Okay. I apologize, it is a high res. Okay, all is right in the world. Okay, here we have some M&Ms on the screen. Imagining there are other parts, or maybe they're going into cookies or something, but we need to determine if these two yellow M&Ms are far enough apart. For some reason they need to be a certain distance, or have a certain distance between them. So in this one, we're going to put the safe distance in the background script, and at startup, it's going to put that criteria and two different messages and two registers. And in the foreground script, we're going to inspect the image, compare the distance measured to the safe distance, and display a message in the result table. This is pretty similar to the one we just did. I'll go through it rather quickly. I'm going to open up the background script first. Make sure that's correct. That's nice, all the code's filled in. I wonder if I opened up the instructor version. Okay, well, we have all the code. It's here written for you. We've got a pass message and a fail message, and our test criteria is 10 pixels apart. We need to have 10 pixels distance between those two M&Ms. We've got those messages in that test criteria. We're going to write the messages to registers 1100 and 1200. We're skipping 100 registers between those two. Because these strings are pretty long, we can change them on the fly to anything else. So by giving us 100 actual registers between those two different strings, we can modify that and not have to worry about it too much. And then we're putting the test criteria into register 1300. We go ahead and compile, and that looks great. Let's come over into the foreground script, open that up. Alright. So the first thing we need to do here is retrieve the data from the background, from the registers. I'm going to declare an int. And again, just use your functions over here to grab the data. Okay, so we're getting the test data out, and then in this next line, we are calculating the space taken up by the M&M. So basically what we're doing here is we're adding the two radii together for the two different yellow M&Ms. And we are calculating the distance from one M&M to another. Okay, so we're using this distance container for the yellow distance tool, which I believe is a measure with points and lines tool to basically just get the difference between the empty space between these two M&Ms. And then we just need to determine if it's going to pass or fail. I'm going to do that with a simple if-else loop or if-else conditional statement. I like to copy and paste a lot so I don't spell things incorrectly. Yellow S is the name of our script self-censor, so I'm basically just writing to a container right now. And I'm just going to do register read string. And I'm going to pull the passing string out of this register. Okay, and if we don't pass, we fail. So in that case, I'm going to go ahead and pull that fail string out of that register. And by doing it, by putting a conditional statement in here instead of by pulling everything out of the registers and then seeing if we need it, we actually save a little bit of processing time. That can be a good way to write your scripts in the future. Go ahead and compile. Okay, up here we need a semicolon. Yeah, like I said, it's good to copy and paste so you don't spell things wrong. It really helps. And again. Okay. Alright, so this one's failing. The M&Ms are touching. We go to the next image and we're passing here. So again, very similar to the last example we did. I just wanted to point out with this example, people tend to stick around the 100 and 200 register range and kind of forget that you have so many registers available to you. So you can take that number up there pretty much as high as you want. And then don't forget that you can write strings to registers. You just have to be aware of how many characters you have in your string. Okay, so any questions right now? In my next example, we're going to write an array to registers. Is the screen size good? Can everybody still see it?
Yeah, it's fine.
Okay, great. So, cancel. Into emulators again. Change that back to bitmap. Okay, so here are these images. These are coins, but it could be, anything on any part. So basically what we have here is we have a blob tool counting the coins, and we need to create an array of the radii of the coins. We're going to use a for loop to do that. And then we're going to write that array to registers. One thing we do need to keep in mind, though, as we write this, is that we need to account for the changing number of coins in the images. Because remember, with the for loop, we have to kind of know and predefine how many times that for loop is going to iterate. So we just need to take that into account here. So this is just going to be a foreground script. Okay, so I'm going to start off declaring some variables. I have an integer called numCoin, another one I, and another one j. I'm going to use those for the loop. I have a double. I'm going to call that radii, and that is going to be a variable, so I'm going to do open and close square brackets. So I've just declared a variable called radii, but I still have to construct that array. And we'll get to that in just a second with the assignment, after the assignment. But for numCoins, we're just going to make that the numBlobs parameter of the blob counting self-sensor. I'm just going to open up CoinCount, which is the blob counting self-sensor, and double click on numBlobs. So the number of blobs is the exact same thing as the number of coins. I'm just putting it into a variable so I can more easily manipulate it. Sorry guys, I hit mute accidentally. The next thing I'm going to do is add this radius, the radii, to the array. So I'm just going to write the array in this one. And for that I'm going to say radii, and then I'm going to put I in the square brackets so that we're updating the numbers incrementally as I increment. I'm going to say coin count equals Bob's information, and one of the parameters down here is radius. And I'm going to put I in here as well. So we're, for blob 1, we're assigning the radius of blob 1 to member 1 of the radii array. And for blob 2, it's member 2 of the radii array. Okay. And then we also want to write these to registers. And one of the things I'm going to use for that is this J variable. I'm just going to say J equals I times 10 plus 100. And I'm going to use this J variable basically to stick 10 registers between each variable that we're writing. So just typing that out, I'm just going to grab it. Let me register write double. And for the register number, it's going to be J. And then for the variable, it's going to be radii I. Okay, so in J, we're basically taking whatever I is times 10 plus 100. So when I equals 0, we're just going to, which is the first member of the array, we're going to write that member to register 100, which is J. And then for the next increment of I, which is 1, we're going to write the radii as a member 1 of the radii array to register 110 and kind of keep going up from there. Semicolons are indeed helpful. Okay. That looks good. Now let's check it. Go into communication settings. And I'm using NLX version 1.3 beta 4, where we have kind of merged the communications window into the System Explorer window to just kind of give you one central location for accessing everything. And we're going to access the registers in the custom drivers section, and I'm going to come under DB2 registers. And so I said I was writing to register 100 to begin with, and I'm actually going to go ahead and inspect, kind of keep going through here. I'm going to stop here. So this data is pretty much unintelligible. In register 100, we've got 64, 73, and 101. This doesn't mean anything to us. We're just trying to write a register, or write a radius to this register, and this is very confusing. So that's where the tags come in. So for tag 1, we're monitoring, so we're just looking at what's in that register. We're starting at register 100, you can see that right there, and then by selecting this data type, that determines how many registers after 100 it's going to look at. So if I were to change this to a byte, it wouldn't look at anything but register 100, and we get 64, which isn't our value. It doesn't make any sense. So put that back to a double, we go from 100 to 107, and 50.181 is where it's at. So that's the radius of the first coin, which should be this one. Okay, and so then tag 2 right here is going to be the radius of the next coin. Tag 3 is going to be the radius of the third coin, and on and on and on. So the data is stored in registers, but that data doesn't make any sense to us in this window, so we create tags to interpret the data. Any questions on that or on arrays and storing arrays to registers? All right, I'll go on to the next part, which is communication. I'm going to go and share. All right, so let's go ahead and dive into communications. In this section, we're going to go over the structure of the virtual memory in the DB2 system, and I'll explain what that is, the advantages and purpose of the different input and output commands, and the structure of the various forms of memory within the system. I'll just kind of graze over those. So for your I/O sources, you have your physical I/O, which is 8 configurable I/O points on the DB2 Con I box. You get 8, and they can be inputs or outputs. You get the Ethernet I/O, which is the Con IOE, and has 8 inputs and 8 output signals. You can add additional modules to that. The multi-purpose DB2 registers, which we covered just now with the register write and the register read. The Modbus registers and Ethernet IP, which is where the virtual I/O is mapped and individual signals can be read or set through implicit messages. That's what we're really going to get into here. Okay, so for accessing the I/O registers, which again, we're talking about the virtual I/O here, not the actual I/O, not actually pin 8. I'll show you how to link the virtual I/O to the physical I/O. But again, this is all virtual. We need to use a long data type. You can use this assignment method, long input 24 state, and another one, B equals 1. You have input 24 state equals get input, and B 24, which is how you access the actual bit. Okay, and then there's the direct method, which is the one I'll be using, the one I'll be showing you. It's just get inputs and then 1L less than 24, which is just saying get the input in coil 24. Okay, so to make this make a little more sense, again, scripts don't actually access the I/O. They access the virtual I/O, which is where all the system inputs and outputs are saved. Any one of these inputs or outputs can be manually mapped to the physical I/O by the user, and I'll go over that. And the virtual I/O can also be accessed via Ethernet by accessing specific system registers. So here's a good schematic of the virtual outputs and the virtual inputs. And I'll show you where to find these in help files as well. Okay, so here's the virtual inputs. This slide is hard for me to see. So let me see if I can zoom in. That helps. Oh, what I wanted. Okay, that's still a little hard to see. Let me show you where to find this mapping in the help files. That should be a little bit bigger for us. Let me actually share the help files. Can you guys, I'm gonna mute you. Can you see the this help file page?
No.
No? Okay.
Inlet needs to be dragged over. There we go.
You can see it now?
Yeah.
Okay. In this, just going into content, I'm going to make everything go away. And in Chapter 8 is the input-output functions. This is a good reference for any of these that I'm going to talk about today. But at the bottom here, you have DB2 register and IO maps. Make this a little bit larger.
Oh.
Hello?
I'm sorry.
No problem. Okay, so up here, we're looking at the virtual output signals. I don't know if you guys can see this, but you could go into your help files. Any of the versions of Intellect are going to have this. Under Chapter 8, the DVT register and IO maps. And up here, we've got the virtual output signals. And we have all of our reserved registers here. And then down here, we have the input signals. So let's look at the output signals. This 1L is the trigger acknowledgement. 1L -1 is product select pass. Here we have with 3 and 4 pass and fail. So you get a lot of these, and then we come up and we have the strobes, and some of these are reserved, and then we have the users 1 through 16, and we also have scripts 1 through 16. And in the input, the first one we have is trigger. The second one is product select. Quadrature input. Anything you can access the digital I/O is here. We have the digital relearns 1 through 4, the product ID bit, and then also users. User 1 through user 32. So that's what we're looking at. Let me go back to PowerPoint. Okay, so there it is again. All right, so we're going to go to the inputs first, and there are 3 main functions that you can use with the inputs. We've got get inputs, so get whatever input is in the coil we're trying to access. Wait on input and wait on any input. So I'll go over these a little bit more. And basically what we're doing with these is bit masking by saying this b less than 6. We're actually just saying only look at bit 6. So we're blocking out all this other data and we're only looking at what's going on right here or wherever we are. Okay, so for get inputs, these are available in the foreground scripts and the background scripts, and it gives the virtual input status at the time it's called. So if it's high or low, it's just depending on when this, whichever script accesses this data. And again, we use the mask that I just showed you in the last slide to just isolate a part of that register to see what's going on. So down here we have a byte that we're calling my data. we're saying if the input in register, or I'm sorry, bit 32 is not 0, then we're going to go ahead and read register 200. If it is 0, as in if it's not high, we're not going to read that register 200. So really, we're just checking there to see if it's high or low. So you can, wait for a signal to come in, and we'll go over that in just a second. And when that signal comes in, execute a certain part of your code. Okay, and for multiple signals, you could just do if and get inputs just tells us that we're looking at the inputs and we're trying to get the value out. We can have, or we can look at bit 32 and we can look at bit 33 using the ampersand, which is our and symbol. If both of those are high, then we're going to go ahead and read register 200. And so that's looking at these right here. That's what we're looking at. So everything else is blocked out. We don't care what it is. We just care what these two are, 32 and 33. Okay, so that's just grabbing whatever is in those registers. Then we can wait on an input. So this is used only in the background script because it interrupts everything else. It stops the code and waits for whatever register you're looking at to go high or go low. So it acts like a break, and you get a 0 for success and a negative value for failure. And a result of negative 12 is reported for timeout. Okay, so here we have two variables, result and value. Results an integer, value is a byte. And we are, the structure of this function is wait on input, and then the first value in the parentheses is the bit you want to access. And the second value isn't register, it's actually the timeout. How long you want to wait in milliseconds. So here we've got result equals wait on input. We're waiting on bit 32, and we're going to wait for 150 milliseconds. If we go above 150 milliseconds, we're going to get a value of negative 12 here. And if it's successful, we are going to get a 0. So then we can say if it was successful and the input was received, then we'll go ahead and read register 200. And then there's a function called wait on any input. And this one allows you to monitor rising and falling edges, and you can monitor multiple inputs at one time. It also allows you to toggle for a certain amount of time instead of going high and staying high for code to execute, and it is the preferred method. So with this one, it's also used only in the background script because it acts like a break again. It'll hold at the line of the script until the input goes active, inactive, or timeout. So again, on any input, if it's high, we're waiting for it to go low. If it's low, we're waiting for it to go high. So we've got that results and value again, those two variables. And we're saying result equals wait on any input. And we're looking at bit 32. And for -1, we use -1 when there's no timeout. It'll just stay here until that happens. Now, notice here that we've got this 0L, comma, then this 1L minus 32. What we're saying here is we're waiting for bit 32 to go low. If it were in this position, it would go high, and everything we've been looking at before has been high. So here we're saying, because we've got the 0L before the bit 32, we're waiting for bit 32 to go low. And on the next line, we're waiting for bit 32 to go high. And again, we're waiting forever. So basically, the script is saying, I need bit 32 to go low and then go high. And if I still have the result as 0, then I'm going to read register 200. Okay, so to do wait on an input with multiple inputs, same code here, and we're waiting on any input in bits 32 or 33 to go high, and we're going to wait forever, basically is what that means. And again, if we had a 0L here and we had all of this with bit 32 and bit 33 right here, that would mean we're waiting on it to go low. So the first position is high, the second position is low. And then if our result 0 is successful, we'll go ahead and read register 200. Okay, any questions before I go on to outputs? Any questions about this bit masking concept? Okay, I'll go on to outputs, and we'll talk about the various functions there. Again, if you need to ask a question or tell me something, you can press *7 to unmute yourself. Okay, so here's the output architecture again. We start down here with 1L and work our way up. The three output commands I really want to talk to you about are get outputs, set outputs, and set outputs after inspection. For get outputs, you can access these in foreground or background scripts because we're not holding up the script. We're just seeing what, if it's high or low, seeing if a certain bit is high or low. It's going to give the virtual output status at the time it's called. And we use the bit masking concept again to grab that. So here we want to see in the outputs part of our memory, we want to see what's going on in bit 8. So we're going to block out everything else and just look at bit 8. So same thing as bit inputs, but we're looking at the output part of the memory. So for set outputs, again, it's not holding up the script, so it's available in foreground or background scripts. And we're going to write this in a very similar way to the, I'm sorry, we didn't have set inputs. So this one's unique to the outputs. Because it's an output, we can set it where we're kind of limited with the inputs. So what we're doing here, this is where that kind of high or low really comes into play. If you have the bits or the bit or the bits that you want to access in the first position in the parentheses, i.e. before the comma, then you're setting them high. If they're after the comma, you're setting them low. We still need to have this 0L here to indicate that it's going high. So with this one, we are setting bits 48 and 49 high, and then we're waiting 10 microseconds, I believe. I'm sorry, 10 milliseconds. And then we are going to set them low again. And so here we show them low. This is after the script has already executed. So we're just basically toggling these. We're setting them high, waiting a tiny bit, and then setting them low. And we're doing that with the set outputs function. Okay, set outputs after inspection. You can, again, use this in the foreground or the background script. And it's going to set the virtual outputs when the other outputs go active. And again, we're using this bit masking concept. So here we've got this max distance in pixels equals 3.65. If the whatever this height self-sensor is, if the distance measured by the height self-sensor is greater than this max distance in pixels, then we're going to set outputs after inspection. We're going to set output 28. Okay, another thing we can do with the communications part of scripting is to go ahead and work on we can access digital relearn, and these are input bits 8 through 11, and we're going to toggle the digital relearn input bit, which is input 8. So we're going to set inputs. We're going to set inputs with bit 8, and we have the 0L to indicate that it's going high. And we're going to wait 5 milliseconds, and then we're going to set it low again. Okay, and so to trigger the inspection, you can do this in your scripts as well with the set inputs command. We're going to go ahead and, it shouldn't be digital relearn, we're going to go ahead and toggle the trigger bit, the trigger input bit. We're going to have 1L less than 1 in the high position, 0L in the low position, wait 5 milliseconds, and then set it low again. You do have to be aware that triggering an inspection can stop the background script because the background scripts have lower priority than acquiring and inspecting images. Doesn't happen a whole lot, but just be aware that there's a priority system in the camera, and you can potentially stop the background script. Okay, so wait on first user. We can wait on user 1 to go high and then trigger inspection. And basically what we have here is we are waiting forever for user input 1 to go high. So we have result equals wait on input. And when it goes high, or if it goes high, we have register read by 200. So that's just an example of how you can use any of these and create basically your own functions based on which bit you're accessing here. Okay, so these register spaces are volatile memory. The spaces available with this are the DVT registers, the Modbus registers, and the Ethernet IP registers. Okay, so again, all register spaces that are not reserved for the system functions are independent and do not overlap. Data types are assigned accordingly when applicable. So if you're using the DINT registers, you can only use integer tags, that kind of thing. And in most cases, when you're accessing or when you're using the tags, the individual correct register size is automatically configured for you. And the virtual I/O is fully mapped to several of the register spaces. So just to recap real quick, we have the multi-purpose DVT registers. The first 32 of these are reserved for I/O signals, which is basically what we were just accessing with the bit masking. And then the other are predefined values. Because we had a chunk of reserved registers that we weren't able to access in there. And then the Modbus registers are the same thing, only all that data is contained in 16 registers instead of 32. And then we have Ethernet IP, which is mostly for Allen Bradley. These registers are again available for general purpose data exchanged through explicit messages. Okay, and so the different commands here, we've seen this register read, byte or integer, register write, byte or integer, whatever it is. For Modbus, it's NB_write and then the type, or NB_read and then the type. And for Allen Bradley, it's AB underscore register write the variable type, or AB underscore register read the variable type. Okay, so just to recap one more time, accessing the virtual I/O means you're accessing the reserved registers. These registers have predefined functions as noted on the input and output maps, and they're shared. These are shared between the DVT and Modbus registers only for this register space. So here's that schematic again. So all of this all the inputs and outputs are contained here, and they're shared between Modbus and the DVT registers. Okay, I think that's all I wanted to cover. Let's go ahead and do some examples. Any questions before I go on to examples?
Jennifer, how many background scripts can you have running at the same time?
I'm not sure there's really a limit on that, because depending on what the background scripts are doing, they could be taking up a lot of the processor or just a tad bit. So it's highly dependent, but a lot. I've seen a couple of system files come through here with a ton of them in there. You just have to be aware that they have less priority. So some of them could be stopped, or all of them could be stopped when the system goes to acquire and inspect an image.
Gotcha.
But it's quite a large chunk of memory with our new cameras with Intellect. When we've upgraded the memory, it's gotten much larger. Okay, in this example, I've essentially got some object locate sensors looking for the letters DVT or JPEGs. Back to JPEG. Reason. Okay, so we're just inspecting this. We kind of recreated this from another inspection we heard about, where they were inspecting the letters on a on a tire, to make sure they were there and readable and everything. So we kind of grabbed some letters and recreated this ourselves. So we're just going to be inspecting and making sure that these letters DVT are there and that they're appropriate, and you know, not missing any parts of them. All right, so for this one, we're actually going to use a foreground script. Okay, and basically we're testing to make sure, again, that the letters D, V, and T are there and correct. And we're going to basically write to pin 2 we're going to set pin 2 high upon failure and keep it low if it passes. And so same thing with the letter V. If the V letter fails, we're going to set pin 3 high, and if the letter T fails, we're going to set pin 4 high. And then for the entire product, we're going to tie that to pin 6. So let's get started. All right, I'm going to put this sleep statement at the end. We're basically waiting for a second, and we're going to give the software time to update so that we can see the changes in the System Explorer window. But I'll just go ahead and get going here. I'm going to say int, I call this signal2 equals 0. I'm just going to define it to 0. Okay, and I'm going to tie these signals to the different pins. What I'm going to do next is just actually output a string to the result table. I'm going to say loader determiner dot string equals result plus I'm going to grab the results from the D object locate sensor. Okay, really my only purpose with that line of code is to debug, to make sure we're getting reasonable data into the result table. I could also use the debug print statement that I showed you guys yesterday. I would just go view that in the script debug window. So I can do it either way, but I just want to get something out of here so I know my data is correct. And basically what I'm going to do now, I'm going to create 3 if statements. They could be if-else statements or if-else-if or you know, either way is fine. I'm just going to do it this way. So I'm going to grab the result for the D letter. Make sure it's not equal to 0. So basically, if it fails, I'm going to make sig2 a 1. Okay, and then all these functions I was just talking about with inputs and outputs are available here, plus some more. So I'm going to say set output, and in this first slot, I'm going to just type the output that I want to set high, because again I'm setting it high. And then here I'm going to put the 0L because again I'm setting it high. I would switch these positions if I wanted to set this pin to low. And again, the 1L here just establishes that this is a long variable type. That's all. Okay, so I've got that. So if we fail, if the D cannot be found, or if it's not the correct D, then we're going to go ahead and set pin 3 high, and I'll show you how we're actually going to tie these to the pins in a second. So we're just going to go through and do the same thing for the D and the T here. I'll just copy this. That T, big 3. This is going to be 33 instead of 32. Make this one a T, make this 64, and make this 34. Alright, no errors. It's going to go slowly on us. Okay, well, while my system is working its issues out, can I answer any questions for you guys real quick? Oh, I crashed it. Okay, what I'm going to do next, now that I've written my script and I'm setting these outputs high, I'm going to go into the physical I/O under System Explorer, the System Explorer window, into Communication Settings, and into Physical I/O, and I'm going to go to Pin 2, and in the Properties window of Pin 2, I can choose a function for Pin 2. So it could be Trigger, it could be Input User 1, it could be Product Select, it could be anything. So I'm going to go in there and actually assign Pin 2 to, I believe, what is... I believe it's User 1. Okay, I'm going to have to restart here. I apologize. Alright guys, I apologize. I'm going to try one more time here. Okay. I'll tell you what, I'll let it kind of work itself out, and I'll go on with the next section of, with the product, the object, and the image object. We'll talk a little bit about that, and in the meantime, I will try to get it working on my system. I always seem to crash it when I'm training. Very annoying. Okay. Alright. Let me open up next PowerPoint. And this next section I'm going to talk to you about will really give you more advanced control of the system. There's some really cool stuff with this. It's my favorite part of scripting. Okay, so we're going to talk about image, product, and window objects. Question. So let me get this audio number for Brian real quick. So, alright, I'll just post that up there for anybody who lost connection and needs to dial back in. On with image and product object. Okay, we're going to go over objects and what they are, the functions of the image, product, and window objects, and the advantages and disadvantages of each object. So you can kind of know what applications they apply to and where they're useful. Okay, so just a couple of the imaging basics for our system. For the inspection process, we acquire the images, then we add them to a buffer, which is the holding place for images until they can be inspected, and then we inspect them. And basically with these objects, we can make changes to the image for inspection, or we can make changes to the product for the inspection. Okay, so for an object definition, for any of you guys who haven't had object-oriented programming before, objects are like VCRs. They have a bunch of, VCRs have a lot of buttons that initiate various functions and features that the VCR is capable of performing: play, stop, rewind, record, whatever. So we have a couple different objects in scripting, and these are analogous to the VCRs. We have the image object. For the image object, we essentially have quotation buttons that you can press that will initiate various functions that the image object is capable of performing. Same thing with the product object. There are different functions it can perform, how to activate those functions. And then there's also the window and the sensor object, and we're just kind of going to graze over those because they aren't used as much as the image and product objects. Okay, so for the image object, we use these in background scripts to give the user more control over inspections. You can control the flow of an inspection. You can control imaging parameters such as illumination, digitizing rates. You can perform multiple inspections on the same image. So if you have 5 different products in your camera and you want to inspect all the 5 products on each image coming through, you can acquire an image, basically hold it there, and run your 5 products over it and let them compute whatever they need to compute, and then acquire another image and go back through all 5 again and again. or you can acquire and perform multiple inspections to achieve an overall result. So you could take an average of, if you're measuring something, you could take an average of 5 different images and inspections to get an overall result of pass or fail. You have a lot of control. This opens up a whole lot of stuff in the camera. So for implementing the image object, there's a very specific process that you follow for this. You want to declare the image object, construct the image object, set the properties of the image object, acquire the image, pre-process the image, inspect the image with a product, and then send the image to the SID. So declare, construct, set, acquire, pre-process, inspect, and then send. So it's kind of a lot, but if you try to set the properties of your image object after you pre-processed it, it does you no good, so you really need to follow that process. So here's what it looks like. At the top, we're declaring an image object, image img, declared. We're also declaring a product object, product p, declared. And then we're going to, we haven't covered the product object yet, but you don't need to construct the product object the way you have to the image object. So we're going to basically set the properties of the product object here with p equals get inspect product. So we're setting the properties of the product object. Then we're going to construct the image object, which is what we're doing right here. Image equals new image, open and close parentheses. This is really similar to what we did for the array, where we had the name of the array equals new, and then the variable type, and then open and close square brackets. Same thing. Anytime you do construction of an array or an object, you're always going to have the word new, and you're always going to have some type of brackets being opened and closed. So then we're going to set the properties of the image object, and one of those properties we can set is the exposure time. We're going to change it to 3 seconds. I believe, actually, I take that back, I'm sorry. With these, you have access to microseconds, so 3,000 here is actually 3 milliseconds. After that, now that we've kind of set the properties of our image object, we're going to go ahead and acquire an image, and that's achieved with just the .acquire function. And then we're going to inspect the image, and we're going to do that with product P, which is why we have this P up here, and we're assigning a product to our product object, which is P. And then we're going to use the image.save function to send the image to the SID. If you forget this, you aren't going to see any of these images show up on your laptop or on your desktop computer because you'll still get the results out of the camera, but they're not going to come through on your system, on your computer system. I apologize. Okay, so for the image object fields, there are a couple different fields that you can use to monitor or change parameters associated with the image. You've got the ID, the image ID, which is a unique number for each image. The exposure time, which we saw in that example I just showed you. The X and Y coordinates. These are the coordinates of the upper left corner and then the coordinates of the lower right corner. The digitizing rate, and the active strobes. And you can get all the details on these in Chapter 11. Okay, so going on for the image object, we do have to, I'm sorry, this is the constructor we have to call to initialize, or what I call construct, the image object. This initializes all products, all parameters according to the settings of your non-product. So if you know that you want every single product in your image, if you want everything with your image object to be inspected at 3 seconds for your exposure time, which would be huge for exposure time, you can go ahead and set that in your non-product, and it'll automatically get imported into your image object. this has no association with a product object, and we'll talk about the product object in a minute. But if you need to use that, you have to declare it and create it separately. So here we are declaring an image object. The name of our image object is my.img, and then we're constructing it with this line, my.img equals new image, open close parentheses. Okay, and then the acquire function, this causes the system to acquire an image with the image acquisition parameters currently contained in the image object. You can set all those specifically for each different image object, or you can just set them for your non-product and have them imported in if they don't need to really change. You can only use this with the external trigger. If you have it on the internal trigger, it's not going to work. So here this line right here, we have an image object that we declared, and then we constructed it on this line, and then we set the exposure time to 3 milliseconds on the next line, and then we are acquiring an image with 3 milliseconds, with a 3 millisecond exposure time here. We're using this result variable to check and make sure this was successful. And I'm pretty sure for all of these that a 0 was successful and a negative number means it was unsuccessful. Okay, so for the save function, we acquired the image. I'll go over inspecting it in a minute, but to saving it, I think it's a tad bit misleading because you're not actually storing the image anywhere. It doesn't get saved anywhere. You can't access it later. All you're doing is sending it to the user interface. So if you're connected with a laptop, you can actually get that image and see what's going on inside the camera. So this function causes the image to be placed in the saved queue. The saved queue contains images that will be sent to the UI, SmartLink, ActiveX, any VB applications you've written, anything like that, when the system has time. After you call this message, or this method, the image object is released and another image can be acquired. Okay, so here's an example. Again, here on this line, we've actually declared and constructed the image object all in one line, set the exposure time, acquired the image, and then if the image acquisition was successful, then we are going to send it to the UI, and if this part wasn't successful, then we're going to get a debug print statement saying error saving. So I take that back. If the results here are 1, is 1, then it was successful. I apologize for that. Okay, so for the inspect function, we are just causing the system to inspect the image using the predefined inspection product. And again, you can only use this with the external trigger. So here we've got a product object named P1, and an image object called my.img. We've constructed the image object. Then we set the exposure time for the image object. We've acquired the image and made sure that we did it correctly. We're getting that variable out. And then we are assigning a product to our product object. We're doing that with get product test 1, and I'll go over all the how to assign a product to a product object in a minute here. And then we want to inspect the image with product P1. So for that, we just say my.img.inspect, and in parentheses is the product that we want to inspect with. Okay, so here's an example. An image needs to be inspected more than once. So we need to create an image object to acquire and hold the image, and then inspect it as many times as needed. The limitation here is every product used to inspect the image will effectively have the same exposure time and lighting conditions. So we can go ahead and solve this. Okay, so we're using a background script, and we're going to wait for the trigger, and then we're going to acquire the image, and then select the product, and we're going to inspect the image, check the results, and see if we need to inspect it again, because this is still the same image. So if we do, we're going to select another product, inspect it, check the results, see if we need to do it again, do that loop as many times as we need to, and we're going to process the results, and then get another image and do the same thing over and over. Okay, so here we have dynamic control over the acquisition by using the image object. Okay, I'm going to go ahead and talk about the product object. This is very similar, and then I'll show you some examples. So for the product object, we use this to access and control products from background scripts. And these are used in conjunction with other objects to further control the inspection process. You can use these independently, but independently without the image object, its functionality is limited. And you can get lots more detail on this in Chapter 5 of the help files in the script reference guide. Okay, so we have some commands for getting products to assign to the product object. So you get product, and this is just going to set the product object used with the product date. Excuse me. So we've got product P. P is our product object. And for P, we are assigning my product to product P. We can also get the image by ID using the digital ID. These are found and assigned in the product manager under the product menu of Intellect. And I believe you can change them there too. So we have product P again, and we are assigning whatever product has a digital ID of 3 to product P. We do need to put this short in here to basically cast this as a short variable. Okay, one other one is get inspect product. This is used to set a product based on the current inspection product. So whichever product you're currently inspecting with will be assigned to the product object. The inspection product can be changed externally using product selection. So you could have a PLC changing the inspection product, which is going to change it with your image object and change your inspection dynamically that way. So here we have product P, and then just P equals get inspect product. So whichever one is the active inspect product will be assigned to the product object P. And then we also have the select function, which is used to set a certain product as the inspection product. So we've got product 1, we're getting the product that has a digital ID 2, and then we are just going to say product1.select. And that is going to change whatever our current inspect product is to this product with a digital ID of 2. And you'll see that change on the product toolbar of Intellect in the drop-down menu. It always currently lists your inspect product. So you'll see that there. And the inspect product causes the system to inspect the image with a predefined product. Again, it's only used with external trigger. What we're doing here is we basically have declared the product object. We've assigned it a product. We have gotten its exposure time using the getExposure function. And there are a bunch more functions listed in that Chapter 5 of the help files. And then we set the exposure type. We use the setExposure function. And then we have made that product the inspect product by this line right here. I know it gets confusing with the select and inspect, but by saying select, you're actually saying this is the inspect product. And then you can actually inspect it with that last line there, inspect. Okay, almost finished here. There's also, and this I use a lot, the next function, and this is used to change a product variable to the next product in the camera. This is determined by the order in which the products were created. So we've got a product object P, assigned it the first product that we have. So while P is not nothing, we are going to set the gain to whatever this comes out to. And then we're going to say P equals P.next, which means go on, get the next product, and assign the next product to product object P, and we're going to repeat the whole thing over and over again. So we are going to basically just multiply all of these products' gains by 1.5. And then the window object, I'll just touch on this briefly. This defines a reduced area of the image, and it's used by the image object and its parameters to evaluate a reduced area of the image. So here we've got a bunch of variables that are going to be our coordinates, and we're assigning values to each of these, and then we're going to declare a window object, mywin1, constructed using that new window, the same way we did for the image object in the array, and we're just going to put in the coordinates of that new window, and then I believe in chapter 13 of the help files, it tells you all the different things you can do with the window object. You can add, subtract, do all sorts of stuff. Okay, so that, in a nutshell, very quickly, are that's the window. The image and product object. So let me try to open Intellect one more time. See if I can get it functioning. Okay, I think I've got it. I can actually hash some of these out. I emailed out to the attendees yesterday the complete DDT script training guide, complete with all of the associated system files that I've been pulling up and the images. And there are Word documents that go with each example that kind of tell you the scope and what kind of results you should see and give you kind of a place to start in writing your script and some hints on how to write it. So I emailed that out to all the attendees. So again, all the examples I'm doing are in that manual. If you unpack, if it's a zip file, if you unpack it, everything should come out with the same file structure that I had it created in. I know it doesn't seem very organized in that zip file.
Did you email that yesterday, Jennifer?
I emailed it to the attendees that were with me yesterday.
I didn't get it.
You didn't get it?
Mike, yeah. And I was in the one yesterday.
Okay. I'll make sure I do that today. I'll just email it to everybody who signed up to set a class.
Awesome.
It was a link to the file on our website.
Mm-hmm.
It's a large file. It takes a little while to download.
Okay.
But yeah, you'll have everything we've just been doing. So let me share Intellect. Get on with this. Okay, real quick, I'll just finish up the example we were working on before we had all the issues. I'm back in Intellect 121 now. On the images. Okay, so this is the instructor system file. I just opened, so it has all the code completed for you. So here's everything I was typing, just a little bit neater. So we've got that all there. So to actually make sure this is inspecting, I'm going to take it off there. So result is 0, and now we've got -11, 0. I'm going to come into the system menu and go into Communications Explorer. Okay, and I'm looking at the virtual I/O right now, but I was trying to tie this to the physical I/O, and what we have here. Value is not changing as it fails. That's because I don't have inspections on. I need to turn inspections on. And now we can see the update for you guys may be a little bit slower on your screen. But as one of these letters fails, the actual pin associated with that letter goes high. Can you guys see that, or have you seen it yet on your updates?
Yeah, looks good.
Okay, so all we did here was with that output 32, 33, and 34 that I wrote to in the script, those are associated with out user 1, out user 2, and out user 3. So we just need to come into the function parameter in the properties window for each specific pin and change that to the actual bit that we were trying to write to. So that's how I did that. Any questions on communications before I get into the product object and the image object? Okay, I'm going to try to move a little bit quickly here. Let's see, I've got 2 examples that I want to get through. Okay, with only 10 minutes left, I'm going to go ahead and open up the kind of answer files and show you guys what I've done here instead of trying to type all this out. Okay, so for this one, what I wanted to do here, and I'm just using the product object in this example. Go into my background script and check out what's going on there. Okay, my script isn't running. Let's take a look at the script. Basically, I've declared an integer, which is going to be the exposure time of the product. Got 2 strings that I'm going to use later. Here I'm declaring my product object. I'm also declaring an integer to hold statistics for the product. And then I'm assigning a product to the product object, the first one in the queue, in the product manager. And so while P is not null, while P is still something, I'm going to get the exposure time of the product and assign it to this variable, product exposure time. I'm also going to get the name of the product and assign it to that string. And then I'm going to get the product stats by calling the stats function, and then I am going to, the stats function is an array. No, I'm sorry. I'm calling the stats function, and in the parentheses, I'm stating which array I want to save the actual values to. And I know that there are 3 parameters to the stats function. And so here I'm just creating a string with each of these values that we saved to this array that I put in parentheses up here. And then I've got a debug print statement to check the product name, product exposure time, and the stats there. And then I have p.next, which says, okay, go to the next product. So So we're starting at product 1, and we're kind of going through here, getting the name, exposure time, and stats of product 1. And then with this line, we're going to product 2 and going through here, and product 3, product 4, and after product 4, we would go on to product 5. And if there were only 4 products in this system file, P would be null then because there wasn't a product 5, and we would actually step out of this loop and finish the script. So that's what we're doing here. What we should see is over to the product manager. Go to the view debug print window. Okay, so here we're getting out product 5, product 2, product 3, product 4, product 5. We're getting out the exposure time that goes with each product and the stats that go with each product. And I'll have to look it up real quick to see what these stats mean again. Any questions on this real quick? The stats function, I haven't pulled it up, I don't have it in front of me, but one of the values is whether or not distance are passed, and I think the other 2 values are possibly the pass count and the fail count. But I would have to look that up in help files if you can confirm that for you. Okay, I'm going to go on to the next one, I believe, the next example. But before I go, let's look at something real quick. Let's go back into my script. And when I looked at the product manager, the inspect product wasn't updating. Let's see what happens when I make the product object the selected product. I didn't get any errors. I just typed that p.select. And now let's look at the product manager. Set a null pointer in line 42. Okay. I'll actually show this to you in the next example, so I'll just go on real quick so you can see the next example, which uses the image object as well. Let me open that up. Again, I'm going to open up the solution here and get to the point really quickly. Okay, so in this example, I've written a background script that cycles through the images and inspects them with product 1. This script also sets the exposure time to 5,000 and saves the image so it will be sent to the UI. It pauses 2 seconds before acquiring the next image, and I've added code that will cause product 1 to become the inspect product. So it's set to product 4 right now. So our inspect product is product 4, so I is next to product 4. I'm going to come into our background script here. And again, all the answers are here. I've got an image object, ing, a product object, p. I've constructed my image object. I've assigned a product to the product object. And then by saying this p.select, I'm making product 1 the inspect product. I'm changing the exposure time for the image object. I'm acquiring the image. I am inspecting the image with product P, and I am sending the image to the UI, and I'm waiting 2 seconds. Okay, it would help if I started the script. I swear, it's raining here, and so it's just not my day. Okay, so you see, once we did this, that product 1 became the inspect product. Now I can change this to product 2, compile, press OK, press yes, and now product 2 is the inspect product. So that's a good example of how you can do this on the fly and make really quick changes really quickly without interrupting inspections, because again, the background scripts don't have anything to do with your inspections. Okay, it's 3:30. Do you guys have any questions?
A lot to absorb.
Yeah, I blazed through it, but my hope is that now you at least know where to go and where to look and where to start with these. And you have all these slides that kind of brush over it again, and of course you always have DBT tech support.